Notation and symbolism for subsets. So let's begin our discussion on notation and symbolism, specifically as it relates to subsets. Welcome to this section. As you know from our previous discussions, sets are fundamental building blocks in mathematics. Now, to communicate effectively about these sets, and especially how they relate to each other, we need a standardized way of writing things down. That brings us to the first point on this slide. In mathematics, using clear and concise notation is absolutely crucial for expressing ideas accurately. Think of it like a precise language. If we're sloppy with our notation, our ideas can become ambiguous or even incorrect. Now, when we start talking about subsets, which, remember, are sets contained within other sets, we use specific symbols to show those relationships. These symbols are a shorthand way of saying things like is contained in or is not contained in. This tutorial is designed to introduce you to those key symbols. We'll not only learn what the symbols are, but also how to interpret them correctly. We'll be working through examples to make sure you're comfortable using them. We'll start with the main subset symbol itself on the next slide, so pay close attention as understanding these symbols is vital for more advanced set theory concepts later on. So let's begin our discussion on notation and symbolism, specifically as it relates to subsets. The subset symbol. So let's move on to the core of understanding subsets. As we discussed on the previous slide, clear notation is really important in mathematics, and now we're going to focus on the specific symbol we use to show that one set is a subset of another. This slide introduces the symbol, which looks like this. It's a small subset symbol. I would pronounce it as is a subset of. It essentially tells us about the relationship between two sets. More specifically, this symbol means is a subset of or is contained in. Think of it like this. If set A is a subset of set B, it means everything inside set A is also inside set B. Now, let's get a bit more formal. We say that if every element of set A is also an element of set B, then A is a subset of B, and we write this mathematically as a subset of B or A with the subset symbol underneath it. So, A then the subset symbol, then B. Keep this symbol in mind because we'll be using it a lot in the examples coming up. Remember, it's all about whether every single thing in the first set is also found within the second set. We'll explore this further with some concrete examples on the next slides and also clarify what this symbol doesn't mean to avoid any confusion. Understanding the symbol. Let's move on to this slide. Now, we've established what the subset symbol, that is, the symbol that looks like a contained within symbol, means, but it's really important to understand what it doesn't mean. The first point here is that the symbol, which we read as is a subset of or is contained in, does not imply equality. This is a very common mistake students make. Just because set A is a subset of set B doesn't mean that A and B are the exact same set. Remember, in the previous examples, B often had extra elements. What it does simply state is that all of the elements of the first set are also found within the second set. Think of it like this. Everything inside the smaller circle, representing set A, is also inside the larger circle, representing set B. And crucially, the second set, set B, is allowed to have additional elements that are not in the first set. Set A, it can contain extra things. This is perfectly acceptable and doesn't invalidate the subset relationship. We'll see this illustrated further in the examples that follow, but keep this distinction in mind. Subset doesn't mean equal. It just means contained within, potentially with extra elements allowed in the larger set. Let's move on to this slide. Example 1, illustrating A subset B \. Let's solidify our understanding of the subset symbol, which we've just discussed. This slide presents an example to illustrate how to determine if one set is a subset of another. We're given two sets. Set A, which contains the elements 1 and 2, and set B, which contains the elements 1, 2, and 3. Remember, a set is just a collection of unique elements. Now, to determine if A is a subset of B, and we write that as A is a subset of B, we need to check if every element in set A is also found within set B. Let's break it down step by step, just like we would when solving a problem. First, we identify the elements of set A as stated. Those are 1 and 2. Next, we check if each of those elements is also present in set B. Let's start with 1. Is 1 in set B? Yes, it is. Now let's check 2. Is 2 in set B? Yes, it is as well. Therefore, since we've confirmed that all the elements of set of both 1 and 2 are also elements of set B, we can confidently conclude that A is a subset of B, and mathematically, we write that as A is a subset of B. This example is crucial because it shows us the practical application of the subset symbol. Keep in mind, as we'll see later, that just because A is a subset of B doesn't mean they are the same set. B can contain extra elements, as it does here with the 3. We'll explore that distinction further, but for now, make sure you understand how to verify the subset relationship by checking each element. Example 2, illustrating a case where A backslash N subset B backslash. Let's look at another example, this time to illustrate a situation where one set is not a subset of another. Here we have two sets. Set A, which contains the numbers 1, 2, and 4, and set B, which contains the numbers 1, 2, and 3. Now, remember from the previous slides, for it to be a subset of B, every single element in A must also be found within B. Let's check if that's true in this case. Let's break it down step by step. First, we identify the elements of set A as we just stated. Those are 1, 2, and 4. Next, we need to check if each of those elements is also present in set B. Is 1 in B? Yes, it is. Is 2 in B? Yes, it is as well. But what about 4? Is 4 in B? No, it is. 4 is not an element of set B. Therefore, because we found at least one element, in this case, 4, that is in A but not in B, we can conclude that it is not a subset of B. We represent this mathematically by writing A is not a subset of B, and the symbol we use for not a subset of is a subset symbol with a slash through it. So, we write that as A with the not a subset of symbol, and then B. This tells us definitively that it does not fit the criteria to be considered a subset of B. Keep this in mind as we move forward, because understanding when a set isn't a subset is just as important as understanding when it is. And remember, in the next slide, we'll be formally introducing that not a subset of symbol. The not a subset of symbol, backslash N subset . Let's move on to this slide. As we just saw in the previous example with sets A and B containing the numbers 1, 2, and 4, we introduced a new symbol. This symbol is read as is not a subset of. You'll see it written as a subset symbol, but with a line through it. Now, what does this symbol tell us? Well, it's used specifically when we want to indicate that one set is not contained within another. More precisely, it means that there is at least one element in the first set that is not present in the second set. Remember, for a set to be a subset, every single element needs to be found in the larger set. If even just one element is missing, we use this, not a subset of symbol to show that relationship. This is a crucial distinction to understand as we continue working with sets and their relationships, and it will become very important when we start looking at more complex set operations. We'll build on this concept in the following slides, so make sure you're comfortable with what this symbol represents. Important note, empty set and subsets. Let's move on to a slightly unusual but very important concept regarding subsets. This slide deals with the empty set. Now the empty set, and we denote it as either a capital phi, which sounds like phi, or as curly braces with nothing inside, represents a set containing absolutely no elements. So, it's a set with nothing in it. This slide states that the empty set is a subset of every set. I know that might sound strange at first. You're probably thinking, how can something with nothing in it be part of another set? But bear with me. Remember from earlier slides, for set A to be a subset of set B, every single element in A must also be in B. Now, the empty set has no elements. Because it has no elements, the condition that every element of the empty set is also in the other set is automatically considered true. It's a bit of a logical trick, but it's a fundamental property of sets. Think of it this way: there's nothing in the empty set that could possibly not be in another set. Let's look at the example. We have the empty set is a subset of the set containing 1, 2, and 3. Because the empty set has no elements, it satisfies the condition to be a subset of any set, including this one. This concept will become useful when we start looking at more complex set operations, so it's important to grasp it now. Don't worry if it doesn't immediately click. It's something that becomes clearer with practice. Next, we'll recap the key takeaways from this entire section so you can solidify your understanding of subset notation. Key takeaways. First, we have A is a subset of B, which we write as a subset of B, remember. This means that every single element found within set A must also be present in set B. If you can find even one element in A that isn't in B, then A is not a subset of B. Next, we have A is not a subset of B. Denoted as A is not a subset of B, this simply tells us that at least one element of set A is not found within set B. Finally, and this is a bit of a tricky one, we have the empty set. The empty set, which we represent as either a symbol that looks like a curved zero or curly braces with nothing inside, is a subset of every set. Now, that might sound strange, but think about it logically. The empty set contains no elements. Therefore, the condition that every element of the empty set is also in the other set is automatically satisfied because there are no elements to check. It's a fundamental rule in set theory, and it's important to remember it. Let's recap the key ideas we've covered regarding subsets. This slide summarizes the main points, and it's important you have these firmly in your mind as we move forward. It's the negation of the subset relationship. Just one missing element is enough to make this statement true. We saw this in action with our earlier examples, where we identified cases where one set wasn't contained within another. Keep these 3 points in mind, as we'll be building on them in future lessons. Now, on the next slide, we'll discuss some common mistakes students make when working with subsets, so you can avoid falling into those traps. Common mistakes. The first point here says, confusing subsets with equal sets. Now, remember from the previous slides, when we write A is a subset of B, which we read as A is contained in B, it simply means every element in A is also in B, but it doesn't mean A and B are exactly the same set. They could be different. Think of it like this. If A is a subset of B, it's like a smaller container fitting inside a larger container. The larger container, B, can have extra things in it that aren't in A. If A and B had exactly the same elements, then we would say A equals B. So, just because A is a subset of B doesn't automatically mean they are equal. We call a subset that isn't equal to the original set a proper subset. Now, the second point is about being thorough. It says, forgetting to check all elements. This is a really common error. When you're trying to determine if A is a subset of B, you absolutely must check every single element in set A. You need to confirm that each and every one of those elements is also present in set B. If you find even just one element in A that is not in B, then immediately you know that A is not a subset of B. You don't need to check any further. It's an all-or-nothing situation. Remember our example earlier where A contained the numbers 1, 2, and 4, and B contained 1, 2, and 3? We stopped right away when we saw 4 wasn't in B, and we knew A wasn't a subset of B. Let's move on to this final slide on common mistakes. This is really important because these are the areas students often stumble with when first learning about subsets. So, to recap, double-check that you aren't assuming subsets are equal, and most importantly, make sure you verify all elements when determining if one set is a subset of another. If you keep these 2 things in mind, you'll be well on your way to mastering this concept.